Okay, the last video on resistive networks did not work very well, so I'm going to do a new one that will hopefully not cut out on sound. So this should help you. I'm going to use the same example as was used in the last video, so I'll draw it out here. You have a 10-volt power supply. You have that power supply connected directly to a 60 ohm resistor. And then you have that network connected to a set of series resistors valued at 5 ohms and 15 ohms. And we want to determine several things. One is the equivalent resistance between these two terminals is seen by the battery. So if I took the battery away, what would the equivalent resistance be of that network? And I want to find the voltage across each resistor. So V1, 2, 3, where I could call this one R1, R2, and R3. And also the current through resistors 1, 2, and 3. So those are the things I want to find. I guess I could also find the total current coming out of the battery too. Alright, so that's what I'm going to do. So let me start with the equivalent resistance. So the way I do that is I find the things that I know are in parallel or in series, and I simplify them, and I redraw the circuit for each of those cases. So the first thing I'm going to look at is this series network of resistors here. I have a 5 ohm in series with a 15 ohm resistor, so I'm going to simplify that to a 20 ohm resistor. So I'll create a new slide, and I'll draw the same, everything out the same. Whoops, I'll go with black. And I'll have the 20 ohm resistor here, plus minus 10 volts. And I'll have, whoops, that's not 20 ohms, that's 60 ohms. And I have now my 20 ohm resistor in parallel with a 60 ohm. Remembering that this 20 ohm resistor is really the 15 ohms and the 5 ohms in series, but that simplifies to 20 ohms. So now I can use my parallel resistance formula to determine what is the resistance of this parallel network of resistors right here, the 60 ohm and the 20 ohm. So I'll find that the equivalent resistance is equal to 1 over 60 ohms plus 1 over 20 ohms. If I do the math here, I get 1 over 60 plus 3 over 60, which is equal to 1 over 4 over 60, which is equal to 60 over 4, which is equal to 15 ohms. Alright, so that's the actual parallel equivalent resistance right there. I found one of the things I'm looking for. So new slide. Oops. So in my new slide, what I'll have then, I'll redraw the same circuit, but with a parallel resistance equivalent in it. That is the 15 ohms. And so this is our equivalent. What I can find too at this point is I can find the current passing through that 15 ohm resistor. I is equal to V over R. So I have 10 volts divided by 15 ohms. So this is I total. This is the total current leaving the battery. That's equal to 0.667 amps, or 667 milliamps. That's the total current. Now I'm going to go backward. And by the way, what's the voltage across this resistor? Since we only have one resistor connected to the battery, it has to be 10 volts. That's, by the way, the voltage that I used here. That is the 10 volts. It's this one, although it's going to be the same as the battery voltage. Now I'm going to go backwards and figure out what the current is and the voltage is across each of the other resistors. So I'm going to undo what I just did, redraw my circuit again. 10 volts, 60 ohms, 20 ohms. Now, just like in the last problem, remember this is the 15 ohm resistance right here. So what I could say is that across both of these resistors I have 10 volts. There's 10 volts across this one. There's also 10 volts across this one. If I took a meter, I would be able to measure that. So I could also find the current through each of them using Ohm's law. So, for instance, the current through the 60 ohm resistor, which is equal to I1, is equal to the voltage across the 60 ohm resistor, which is 10 volts, divided by 60 ohms. So, whoops, let me be consistent here. And this is equal to 0.167 amps, or 167 milliamps. Similarly, you could find the current through the 20 ohm resistor. I'll call that, by the way, I'll rename this resistance here, since it's really the series combination of a 15 ohm resistor and a 20 ohm resistor. And a 5 ohm resistor, I'll say it's R23. I'll call that one R23, and I'll call this one R1. But I could say that I23 is equal to V23 divided by R23, which is equal to 10 volts divided by 20 ohms, which is 0.5 amps, or 500 milliamps. So if I were to then try to figure out what is the current through each of these resistors that actually, by the way, the 20 ohm resistor makes up, which is the 15 ohm and the 5 ohm, I would say that through each of those resistors there is 500 milliamps flowing. So I've actually found I1, I2, and I3. I'll summarize that on the next page. Let's say, first of all, R equivalent we found was 15 ohms. Could say I1 equals 167 milliamps. I2 equals 500 milliamps. And I3 equals 500 milliamps. Just to remind you the original circuit, I'll try to fit it in here. $60 ohms. 15 ohms, 5 ohms. So I have 500 milliamps going through here. And I have 167 milliamps going through here. And if you notice, earlier on we found the I total. That was the sum of these two. We could say I total is 667 milliamps, which is what we found earlier. It's the sum of these two. It's also what we found when we just found the equivalent resistance and determined the current that must be flowing through that equivalent resistance. So now let's find V1. Do that up here, and I'll do it in a different color. could say V1 equals R1 times I1. We already know that that's going to be equal to 10 volts. So if I multiplied 60 ohms times 167 milliamps, I'd get 10 volts, but I also know that this voltage is the same as that voltage. That's going to be equal to 10 volts. Either way you do it. Now the more interesting case here, V2, is voltage across the 15 ohm resistor. V2 is equal to the 15 ohm resistance times 500 milliamps, so I could say R2 times I2, R2. That's equal to 15 ohms times 0.5 amps, or 7.5 volts. V3 equals R3 times I3. I3 is the same as I2. That's equal to 5 ohms times 0.5 amps. It's equal to 2.5 volts, as it has to, because this voltage plus this voltage has to equal the 10 volts here. So we have going up 10 volts here and going down 10 volts across the combination of these two, ending up back here at the same potential that we started at. Okay, I hope this helps you in your studying.